Hey everyone, and welcome to this explainer on the invisible tug-of-war that is aerodynamics. Today we're diving right into the whimsical, invisible physics that keep heavy metal machines dancing in the sky. If you've ever looked up and wondered exactly what is going on up there, well, you're in the right place. I mean, think about it. How exactly does a machine weighing hundreds of thousands of pounds just float on invisible air? We're skipping the basic magic tricks today and diving right into the actual physical forces. It isn't just luck. It is a beautifully balanced mathematical dance. Take a massive Boeing 747, for example. It looks like it's effortlessly gliding, right? But in reality, it's locked in a perfectly balanced, invisible tug-of-war with the atmosphere, constantly negotiating with the air around it to stay airborne. Part 1. The invisible tug-of-war. To really get this, we need to meet the four main characters of aerodynamics. Every single flight is basically a constant, high-stakes conversation. You've got lift pushing up, weight pulling down, thrust pushing forward, and drag stubbornly pulling backward. As a pilot, you are essentially the moderator of this intense physical debate. And when all these forces pull equally against each other, boom, the airplane hits this beautiful state of equilibrium. We call it straight and level cruising. You aren't accelerating, you aren't slowing down, climbing, or falling. It is just perfect physical harmony. Moving on to part 2, the great lift-a-dates. Now let's talk about how wings actually conjure up that upward force we call lift. Believe it or not, scientists actually argued about this for a very long time. On one side, you had folks backing Bernoulli's principle, the idea that speeding air over a curved wing lowers the pressure on top. On the other side, Newton's third law fans argued that a wing deflecting air downward creates an equal upward reaction. But wait. Before we solve that, we have got to bust a major myth. You've probably heard of the equal transit time theory, right? The one claiming air molecules on the top and bottom of a wing just have to reach the back edge at the exact same time. Yeah, entirely false. Throw that out. The air on top actually travels way, way faster than that. So back to the debate. The plot twist here. Both Bernoulli and Newton are completely right. To generate lift, a wing has to satisfy both laws simultaneously. You're conserving mass, momentum, and energy all at once. You absolutely need the pressure differences Bernoulli described, and you need that flow-turning force Newton described. They're a package deal. All right, part 3, creating forward thrust. Obviously, to get that air flowing over the wings to create lift in the first place, the aircraft needs a massive push forward. Enter the engines. Modern jets create this thrust in 4 surprisingly simple steps. They take air in at the front, squeeze it incredibly tight with a compressor, ignite it by mixing it with jet fuel, and then blast those high-energy hot gases straight out the back. And as those hot gases rush backward out of the exhaust nozzle at insane speeds, the airplane is thrust forward. It is literally Newton's third law in spectacular, noisy fashion. You push the air backward, the air pushes you forward. Which brings us to part 4, maneuvering an aircraft. Because let's face it, we rarely just fly perfectly straight and level. What if we want to climb, descend, or turn? We have to disrupt that perfect equilibrium we talked about earlier. And whether you're flying a simple fabric hang glider or a cutting-edge fighter jet, you maneuver using the exact same principles. You alter the local shape of the craft to tip the balance of our 4 forces. By adjusting control surfaces, the pilot is actively directing the tug-of-war. Increase thrust and raise the nose, and you climb. Reduce power and let weight overcome lift, and you descend. Or you can bank the wings to tilt your lift vector sideways, pulling the entire airplane into a turn. And that leads us perfectly into part 5, the angle of attack. This is perhaps the most critical chapter in aerodynamics, a hard geometric boundary you just absolutely cannot cross with consequence. Now, this is a common misconception, but angle of attack is not about where the nose is pointing relative to the ground. That's just pitch. Angle of attack is specifically about how the geometric edge of the wing meets the oncoming relative wind. And the magic number here, it's typically around 15 to 20 degrees. This is the critical angle. Go past it, and that smooth laminar airflow over the top of the wing abruptly separates. It just detaches, turns into a turbulent wake, completely destroys your lift, and causes an aerodynamic stall. This is absolutely vital to understand. A heavy cargo jet or a tiny single-engine trainer will both stall at this exact same geometric boundary. That means a stall can happen at 50 knots or 810 knots if you exceed the specific angle. It is an immovable law of physics. An airplane wing stalls because of its angle, not its speed. Understanding this stuff really transforms how you see aviation. It changes the sky from a total mystery into this beautifully choreographed dance of physics, a delicate balance of lift, weight, thrust, and drag. So I'll leave you with this. Next time you look up at a plane passing overhead, will you just see a heavy metal machine? Or will you see an invisible tug-of-war dancing on the wind?